In this video, we're going to survey the types of reflections for a wave on a string. So we start with fixed and free boundary reflections. Then we go to reflections at an interface where two different thicknesses of strings are tied together. And then we're going to talk about the superposition principle and interference for wave pulses that are running into each other. So what I mean by a fixed boundary is that this string is tied firmly at the right-hand side. I'm shooting a wave pulse toward that boundary. And as it turns out, when a wave pulse hits a fixed boundary, it's reflected upside down. In contrast, if the boundary end is free to move up and down, so I could do that symbolically by saying it's just held on by a ring that slides on a smooth metal rod. We shoot the wave pulse at the boundary, but this time when it's reflected, it comes back right side up. Now let's look what happens at an interface between two different thicknesses of string. So you may remember if a string has a larger linear density, waves will move slower in that string. So the first one we're looking at is a fast to slow transition. We're shooting a wave pulse at that interface. While hitting a slower medium is kind of a less extreme version of a fixed boundary, and so it shouldn't be surprising to see the reflected pulse come back upside down. And then the transmitted pulse will go through right side up. I'm going to draw its velocity vector a little shorter because that's the slower medium. Then I look at the slow to fast transition. And again, this is kind of like a less extreme version of having a free end to the string. And it shouldn't be too surprising to see that pulse reflected right side up. Again, the transmitted portion is going to be right side up. One thing I left out of these diagrams is that our reflected pulse should have a lower amplitude than the initial pulse because part of the energy has been transmitted into the second medium. So now we look at the idea of superposition. The superposition of waves on a string, that just means they add like functions. They add point by point when the two wave pulses overlap. So in my first picture, I'm shooting two wave pulses at each other. In my second picture, they're completely overlapped, and what I see there is that their amplitudes are adding. What I haven't shown in the picture is the shape of each original pulse, which is something like this. And I'm going to have two copies of that right on top of each other. What I mean by adding like functions or adding point by point is that I take my y-coordinate on each of those functions and I add them together. Well, each of these has a y-coordinate of 1 at the point I just highlighted, so when I add them, I get a y-coordinate of 2. That's how I ended up with twice the amplitude. I could do this with many points, just doubling the y value, and it builds this large pulse from the two small pulses overlapping each other. When the interference is complete, these wave pulses are going to pass right through each other, and now they're running away from each other. Okay, in this case was called constructive interference, because we built something larger than the original components. Let's get a look at destructive interference. I'm shooting two wave pulses at each other, but one is right side up and one is upside down. And look what happens when these two waves overlap each other. I can see that their y-coordinates are just negatives of each other now. So at the point that I just labeled, I have y equals 1 on one of the pulses, y equals -1 on the other, and those add to 0. And the symmetry continues for all the other points as well. They're all just 0. So the net result is I just get a flat spot at that moment in time. And finally, the wave pulses pass right through each other and then they run off in opposite directions. Now, one interesting question with this destructive interference diagram is what happened to the energy in these waves at the moment the string is completely flat? And the answer is that the energy is actually in the kinetic energy of the string. This side of it's moving down at the moment, this side of it's moving up, getting ready to generate these wave pulses that will run off to the right and left. So why did we just do a survey of all these types of reflections and interference? Where this is going is that we're going to talk about like an entire wave train or a continuous sine function running into a boundary. Every bump on that sine function is going to be reflected, and on the way back it's going to interfere with all the ones that are coming into the boundary. So as it turns out, there are only special wavelengths that will continue to interfere constructively with the incoming waves over time. And these are called normal modes on a string. And normal modes are key to understanding the different sorts of frequencies that you'll observe on a string fixed at both ends. And they're also key to understanding what frequencies you would drive a string at to get really large amplitude oscillations. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.